So yeah, hello again. So now we have 7 people now in the room, so it should be okay. So I can start now, right? So a little bit of announcement. Sorry, I have done all the marking of the midterm exams, and I'm gonna announce it soon in the Google Classroom. But the ranging of grade is around 20 to 30, right? So it's not bad, but it's not good as well, because our full marking is 40, right? So yeah, you should study more for the final exam, okay? For the homework, it should be fine. So your grade should be okay, yeah, if you like pay more attention to the final. Okay, so that's it from my announcement. I'm gonna post your grade on the Google Classroom, and if you have any problem about the scoring system and marking, you can just come to me one by one. I can show you the paper and stuff, so we can discuss how much do you want, or what do you think about my grading and stuff. So cool. Right, let's go over the material now. I think I can finish it in 3 hours. I mean, the whole class, the whole course, of course. But let's see what happened, okay? If not, we can continue on Wednesday, our usual time. Or maybe the better idea is that we can finish today, and on Wednesday we can just go and discuss your question that you have left around, because it's the online teaching, right? You have not much chance to talk to me in real person, so Wednesday should be okay. So let's see what happened, okay? Right. So the stuff that we haven't talked about in the class is the multi-particle state. Okay. This is one of the topics that we have just left, and I'm probably not gonna go over everything, but I will just talk about the stuff that we really need to understand the addition of angular momentum, and that would be my goal for this year. I'm probably gonna left out a lot of materials on the quantum entanglement and the meaning of that and this, or we can discuss it later. But right now we can just focus on the multiple particle states. Okay. So right. Uh, so far in the course, right, what we have seen is just one particle, right? We have seen the state, yeah, describing one particle. Particularly, we are interested in just one electron, right? And spin, obviously, right? For example, we have electron with a spin, yeah. And later we have just learned that these spins are just part of the stuff called angular momentum, right? So we understand how it makes the spectrum of the angular momentum eigenvalue, what is the eigenstate looks like, and stuff like that. Also, obviously, also another one from the harmonic oscillator as well, but that is also one particle state, right? We can describe all the spectrum of the state. Yeah. So how about we want to describe using quantum mechanics to describe the real world, right? Since we know that in real world you have more than one particle, really, right? We often find that we need to describe a system of particles, right? For example, the one that we often see the most is probably hydrogen atom, right? And that kind of system consists of at least two particles, yeah, proton and electron. So in that case, you need at least some kind of new object to understand the state that we have, the multiple particle states, right? So we need a new way, a new object to describe the system. Yeah, so that's a goal. Yeah, let's review how did we do in the case of one particle. Yeah, so for one particle, what we have, the first thing that we have is we use a state, right? We use a state. Yeah, one state. Let's say psi. Yeah, you could do it as a psi as a function of time as well. I'm not talking about the dynamics here. I'm just talking about the state and how to describe particles. So basically just, general stuff for a vector in the vector space, right? And a state is a part of the vector space, right? Sorry. This is a vector space, yeah? And we use this state to describe the particle. And how do we describe it actually? We use an operator, right? We use a physical operator. So that would be T, that would be H, and so on and so forth, right? Okay, sorry, X, P, L. I think I shouldn't mention T. I just use H, P, L, H, and so on and so forth, right? These physical parameters, sorry, these physical operators are just a kind of a mapping, right? This is a mapping from the vector space to the same vector space, in the sense that you have one vector, right? If you have one vector and you act it on using an operator, you change it into another vector psi prime, which is the same object in the vector space V. Yeah. So this is how we actually do it for one particle case. Now the question is, how do we describe it in terms of 2 particles and 3 particles and so on? All right. So let's think about that, right? How about we have 2 particles? Suppose that we have a system with 2 particles and we want to use the same stuff, right? We want to use the same stuff that we described for 1 particle, right? Let's just say that we have psi1 is responsible for particle 1, right? And similarly for psi2, yeah, I'm too lazy for that, for particle 2, right? So let's just say that you have 2 particles that for each one of them, we can describe using a state perfectly, right? For psi1, you can describe particle 1, it's fine. Yeah, everything works fine. You have some other stuff that you describe as well. You want to know the momentum, you want to know the Hamiltonian, stuff like that. You can actually measure it using the state psi1. And another particle psi2, you have psi2 as well, that also perfectly describe the particle 2, right? So each one of them is fine by its own, right? Suppose that we make a particle 1. Let's make a picture, right? Particle 1 and particle 2. Suppose that we have particle 1 and particle 2 in the box, right? Just put them together in the box. And assuming that you don't have any kind of interaction between them at all, right? Just say that, okay, you just leave it freely, just don't interact to each other and stuff like that, right? So what is the total state look like, right? What is the total state would look like? So that's our goal, yeah? So let's make some guess, okay? Since we know that psi1 and psi2 is perfectly fine, right? Since we know that psi1 and psi2 is perfectly fine, you can use it to describe particle 1 and particle 2 separately. So let me guess. How about this? Yeah? How about this? How about we make just a simple addition, right? So state 1 and state 2, state 1 psi1 and state psi2, just do a simple addition, all right? So that would make sense, right? In a sense that you can think about the state that, okay, you have 1 particle, you have 2 particles, you combine them, Therefore, you combine the wave function, right? It looks okay, yeah? Except that it's not true, yeah? Sorry, I should write not true, right? Why, do you ask? So let me give you some example on this, right? Suppose that you have a one system, right? Suppose that you have one is simple harmonic oscillator, right? It's some kind of spring with particle one that kind of bouncing around, right? You have the whole eigenstate and stuff like that. And suppose that two is an electron spin, yeah? I can, right? I mean, that's totally fine. You have one particle that looks like a spring, basically just an electron under some kind of x square potential, basically. And then we have an electron spin, yeah? Then you add them together, right? What happened? You're gonna totally see that this thing, right? The vector space. What is the basis for this vector space describing the particle in the simple harmonic oscillator? How many dimensions you have? Infinite, right? Infinite. Yeah, because you have a infinite steps of the energy eigenstates, right? From n equal to 0 to n equal to infinity. Yeah? So you have infinite number of states. But for electron spin, yeah, for electron spin, the vector space itself has dimension 2, yeah, right? Because you have two bases, yeah, z plus and z minus. Let's say the spin is aligned in that direction or whatever. So it has dimension 2. But the stuff in system 1 is infinite dimension. So therefore, you adding them together doesn't make any sense, right? Because you have two vectors that lies in a different vector space. Yeah. So adding this do not make sense, right? That's it. You cannot use addition for sure. All right. So that's a bit of a strange situation, right? You want to do some kind of addition of two particles, but you cannot do the vector addition. So you can clearly see our difference here, right? So the main obstacle that you have is that the vector space itself shouldn't be equal, like in per se, right? In general case, you can see that the system 1 and system 2 has two different vector space. So if you use the stuff that you can add, you can multiply, you can do some strange thing for one vector space, that's not going to work, all right? So the main obstacle here is that we might have two different vector space, right? And combining them using two different vector space, you cannot do addition, right? You have to do some other thing instead, right? So the stuff that we want to do is that we need to combine vector spaces, right? Instead of combining vector, right? You combine the whole space together. You kind of making them marry to each other and make them a new vector space, right? So we have a new vector space. Yeah. So that's the whole concept of tensor product. You cannot do addition. You have to make the whole vector space, combining them together to get a new vector space that is responsible for describing the system of multiple particles. So that's the goal here, right? That is what we want to talk about today. Okay. So far, so good, no? Do you have any question? No. Good. So, right. Let's define a new way, right? And this new way of doing the two vector space, right? This is for one particle, right? It's for multiple particle. Yeah. So this new way of combining two vector spaces is called tensor product. Okay. So I'm gonna describe the what does a tensor product looks like and the property first, and try to give them physical meaning later. Okay, so that you can be more familiar with how do you do the algebra in the tensor product and stuff like that. Okay, so let's set up some notation first. Let's say that we have let's say that the first particle, right, is in vector space V, right, and the second particle is in the another vector space V. In general, they do not equal, right? They're not equal. Let's say that could be one of the angular momentum, and one would be spin in a different spin, for example, right? Let's say that we have two completely different vector spaces. Okay? We can make, right, another vector space. Yeah, and this vector space is called V. Sorry, V. Huh. V. And using the notation here, right? So it looks like a multiplication, but you have a circular around the multiplication stuff, right? So this thing is called tensor product. Okay? You do cross as a product, and then you circular around the cross product. It's called tensor product, right? So let's talk about the property of the vector space. Okay. Let's say that we have another vector space that called V cross W, right? So the vector, right, in a new, the new vector space, yeah. In this case, the new vector space is called tensor product space, okay? But I can use it quite literally in the new vector space and also a tensor product space as well. The vector in the new vector space sometimes is called this, right? V and W. Okay. So in the sense that if you want to describe a new a new state in the system of particles, you can just use this stuff called tensor product as well, right? So let's assume that we have the same notation for cross. So cross and then circular around it. This thing is a new vector, right? So basically what I'm trying to say is that this, right, leave in this, right? So that's the whole idea. You have a vector space V and you have another vector space W. The tensor product is that you have a new vector space and you have a vector in the new vector space in such a way that V lives in the first vector space and W lives in another vector space. Okay. So basically, we're trying to just put them together and just make up a new vector space. Okay. So this is nothing more than just, let's say that we have a state with angular momentum, we have a state with the simple harmonic oscillator. You just place them together as a state, right? And define the whole mathematics and vector space onto the new system. So this is nothing more than just put them together in the box, quite literally, right? And the box is called tensor product. Okay, so that's the whole idea. So since we have defined everything in the more fundamental level, right? So let's start from the properties. So the properties of the tensor product, right? Let's assume that we have V and W as a tensor product. First of all, right? The thing that we need to do as a vector space is that we need to multiply by a scalar, right? So let's say that these two vector space has a usual scalar number, complex number or real number or whatever. So let's say that. So the first property that we need is that if we have a complex vector space multiply in the first vector, right? So if you scale down the first vector by c, this is equal to scaling down of the second vector as well, right? Since we assume that the two vector spaces has a common field, has a common scalar field, scalar number. Therefore, you have a way of either multiplied by the first vector or the second vector. They should be the same, right? So you can move around the complex number basically. And sometimes you can also write this, right? Because since we have a freedom in writing either on the front or on the back, you can, just commonly draw it out, right? So think about as a common product of two numbers. You can move the C numbers around, right? You can put it in middle, you can put it in front, or you can put it in the front with the parentheses. That's also okay, right? So that's the first property that we need, okay? And the second properties, right? The second property, the tensor product itself has a linear property. What do we mean by linear property? I mean this, right? Suppose that we have two vector in the first vector space, okay? So suppose that we have V1 and V2 are in the same vector space, V, right? And then you combine them together, V1 and V2, and then you do the cross product with another vector from another vector space, W, okay? What do we mean by linear? You have, just a usual expansion of product. So basically you can do this, right? V1 cross W plus V2 cross W. Okay. So this is a linear property because you can actually expand it linearly, right? Also, from the point of view of the second vector space as well, you can guess what happened if we do this, right? If we have two vectors for the second vector space and you combine them, you do the tensor product, you get similarly structure, the linear structure, W1 plus B cross W2, right? So you have a linear properties of tensor product. Okay. So so far so good, right? You have any problem? Cool. So yeah, good. The stuff that we need to talk about after this point is just trying to make sense out of the vector space, the new vector space, right? So as you know, right, if you want to describe it as a vector space, you have to start from the usual properties, right? And the usual properties would follow from these two properties. Let's say if you want to multiply by, a scalar number, that's fine. That is just the first property we have. If you want to do expansion, the associativity and stuff like that, you just use the second property, and that's it. Yeah, the stuff that following is just a comment from the properties of the vector space itself. All right. So I'm gonna go point by point, right? So note, yeah. Sorry, it's a bit too dark. Okay, cool. Uh, the first note, okay. Let's say, I don't know, just a bullet point should be okay. What is the zero vector in the new vector space? Yeah. So the new vector space, right, would have the zero vector that looks similar to the zero vector in each of the vector spaces. For example, right, let's say that I have a 0 here. Yeah. Sorry, 0 here. Yeah. I need to do the addition, right? I need to do the addition, and you get the same stuff. Yeah. Suppose that I want what do you BW U, maybe, I don't know. Sorry. U, maybe, I don't know. Let's say that we have this, right? Okay. I have a very strange way of naming stuff, right? So if we have a new vector v u, can I write this? Okay, it makes more sense, right? Yeah. Let's say that we have a new vector, okay, and this vector lives in the tensor product space v and w, okay. And suppose that I want to do the addition, right? I want to do addition. Now you can clearly see that this 0, bad, sorry. This 0, right, is in the new vector space. Yeah, this 0 is in the new vector space. What do you want from this addition? You want them to be the same, right? Because that's the definition of 0 vector. Yeah. So what do? We do 0, right, plus v cross w, right, equal to v cross w. Okay. Yeah. Yeah, because you have a 0 vector that add to another vector, right? So what you actually want is that, sorry, can I? Sorry, am I not too quick to change the page, right? Are you still following?
Yes, teacher.
Okay, thank you. Yeah, I haven't taught the online teaching for quite a while, so I'm not sure about the the pace. So if it's too quick, just tell me, okay? Yeah. So what do you actually want is that we need to at least have this, right? So 0 vector, right? At least there should be, that should looks like this. Yeah. At least they should look like this. No? No, I mean at least. No. So this is our guess. Yeah. And why is that? Because if you add them together, right? So you can assume that these two addition would work. Yeah. But right now, this is going to be a problem because you are not sure that if we can do this or not. All right. Let's say that this is, yeah. How do we do the addition, right? How do we do the addition between these two stuff, right? So I haven't told you yet how to do it. Yeah. So we are not sure, right? But one thing that we are pretty sure is that, how about this, right? Let's say that if we do this, yeah, if you do this, and then if we add this together, what do you have? What do you have?
V and W.
You can factoring out W because of the second property, right? You can do this, yeah? And what do you have? The same vector, right? You see? So instead of using 0 cross 0, right? You can clearly see that I can just use 1, 0. Yeah? And this is the new 0 that we want. Okay? Yeah. So basically, if we want to define a new 0 in the new vector space, in principle, you can just use 1, 0 from one vector space, and that's it. Whatever you cross product with anything else, that's going to be a new 0 anyway, right? Because of the second property. Cool. And the strange thing is that you can also do the same with the first vector space as well. Sorry, the second vector space as well. Because if you do v cross 0, and you add with another vector v cross w, okay, that's pretty much the same thing, right? You would have this cross product. Sorry. Right? Which result in the same vector v cross w. Therefore, you can clearly see that this is also a vector, null vector, a 0 vector. Yeah. So in this case, you can clearly see that you can just use one of them and it should be okay. Yeah. So therefore, 0 in the new vector space is either this or this, right? They are the same. You can just use them in any way you like, right? Because of the 0 vector in one vector space implies a 0 in the new vector space as well. Are we clear? Right? We can also take a look at this property in a different way, right? So we can think about this, just think about, right? We can think about this as 0, right, is equal to 0 times a new state phi. Yeah. So since we know that 0 scalar multiplied by a vector is also a 0 vector, and this, can be any vector in V cross W. Okay. And if you think about it, right, if you do the first property of the tensor product, that could be anything, right? It could be V cross W or something else, right? And if you multiply them, right, you can use them to multiply the first vector or the second vector. And if you do this first vector, what do you get? You get 0 cross W, which is pretty much the same thing that we have, right? Or you can do the second multiplication here, right? You can move that factor C, which is 0, to the second vector, and you get the same stuff, right? You can also take a look at this way, in this way as well. Okay. So that's my first point. So far so good, right? Okay. So that's the first bullet point, I think. Yeah. Okay. The second one that is more important, I guess, is that you have to think about the new vector space. Sorry, the new vector space W, right? The new vector space itself has a much larger dimension comparing to the previous two, right? Right. The size of the vector space itself is pretty large, right? So what do we mean by this? Okay. What do we mean by this is that if we have a new vector space V cross W, right? So what we expect, sorry, what we might expect from combining two particles is that we just use a state from V and a state from W and do a tensor product. All right. That's typical stuff that I have said earlier, right? You have V in W and V in W, like this one, right? And then we expect that all the states in V cross W can be written in, sorry, I need to change the page. So you expect that if you have a vector V and vector W from the first vector space and second vector space, all the states in the new vector space can be always written in terms of a state in the first one and the state in second one, right? Yeah. And that kind of makes sense, right? Because you have two particles and these two particles can, describe perfectly by these two vector space. You can just, do the tensor product and define the whole thing pretty smoothly without problem, right? But this is wrong, right? So this is not true. It seems okay, right? It sounds like everything works fine if you do this, yeah, and you can claim that all the states in the new vector space is coming from the state in the first vector space and the state in the second vector space. But this is not true, right? Because this is not true. Because V cross W, the new vector space, is also a vector space, right? Because V cross W is also a vector space. Therefore, you have an important operator that is defined in the vector space called additional vector, right? We are allowed to add vectors right? What do we mean by adding vectors? Sure, you can do this, right? If I have psi1, yeah, equal to v1 cross w1, right? And you have another vector, psi2, which lives in the new tensor product space, v2 cross w2, right? If you have these two vectors, right, and you are claiming that the tensor product space is a vector space, you can have another vector psi, let's say psi, right, equal to psi1 plus psi2. You can add the coefficient as well, but that doesn't matter. You can just add them together, right, psi1 and psi2. And what can we write in terms of the vector of the tensor product? That would look like this, right? Yeah. If you add them together, that would look like this. And now the problem comes, right? At this stage, if you go back to the statement that I said earlier, right? You cannot say anymore that for the system of particles, you cannot say for sure that the first particle is in a particular state, right? You cannot say for sure that the first particle is in V and the second particle is in W for any state that you like. Now it's not, right? Because it's a combination of the two. Yeah. So now we cannot claim that psi consists of a state V prime in the first vector and W prime in the second vector space, right? You can you can see that you cannot do that, right? Because they're the linear combination of the two, right? You cannot do that. Yeah. So in general, we cannot claim that for the multiple particle state, you cannot claim that the particle is in a particular state. Not always. You cannot always do that, right? You cannot claim that. Not always, right? So do you see my point? Right? Because you're not so lucky in such a way that you can write a new state psi as a state doing tensor product with another state, right? If you can do that, that's okay. You can call that. But right now, you can clearly see that I can just use some general expression using some general vectors together. You're not necessary in that case anymore, because you cannot always can write that in terms of a state doing the tensor block with another space. Okay, so that's the whole thing, right? In what case you can go back to the case that we talk about, right? So unless we are lucky, right? For example, let's say that W1 is equal to W2, right? Let's say that W1 and W2 are equal, okay? What happened is this, right? Say W1 is equal to W2. You can use the linear properties of the tensor product. And now we can now claim that if we do the property here, right? Now we know for sure that the second particle is in the state W1 and the first particle is in the state V1 plus V2. Okay. Now it's okay. Yeah. Now we can say the state of first and second particle are definite, right? Now we can know for sure that the state of the first particle is V1 plus V2, and the state of the second particle is W1, and that's it, right? We can do that. This is a lucky case, right? In the case that W1 is equal to W2. But in general, you are not going for that special case. Therefore, you can clearly see that what I claimed at the beginning is that the vector space V cross W is much larger than you expect, in the sense that you have the addition of vector space. Sorry, addition of vectors. Are we clear?
Teacher,
Yeah, sure. Go ahead.
since we firstly define that the vector phi should come from v prime times w prime, right?
Yeah.
But if we write v1 times w1 plus v2 times w prime, v2 times w2, okay, we cannot write it in terms of v prime times w prime, right?
Exactly.
So that is a problem. But if w2 equal to w1, we can write in terms of v prime times w.
Exactly. Yeah, exactly.
Okay.
Exactly. Yeah. So you cannot always claim this. So accept that you are so lucky in this case. All right. And there are a whole discussion on this thing. I'm probably gonna spend a lot of time on that as well. If not, I can just continue on later lecture. But this is the point. You have the stuff called entanglement. Okay. And I will come back to this point when I want to talk about a bit later. Okay. But right now, just think about it as a size of the vector space. So the size of the new vector space is much larger than you think. That's all you need to know, right? Because you have the addition of vectors, and that addition of vectors create another layer of complexity to the tensor product, right? So that's good. Okay, so that's the second bullet point that I want to talk about, and then now we can continue on the properties of the new vector, right? And the third bullet point is that the basis of V cross W, right? So we can try to make a basis for the new vector space as well. And not so surprisingly, you can actually construct a basis of a new vector space from the basis of V and the basis of W. Okay. So the new basis can be constructed. Constructed from a bit too quick. The basis of V and the basis of W. Okay. So let's go into detail. Okay. So suppose that we have a basis of a vector space V, right? Suppose that we have a vector basis EI, right? Which is a basis of V. Yeah. And the basis F, right, is the basis of W. Okay. So you have two bases, E and F. Okay. So, and let's suppose that we have a vector V. All right. So let's suppose that we have a vector V, And the vector v can be expanded in terms of summation of the component times a basis e. All right. And you have a vector w, which is expanded in the basis f. All right, because they're leaves in a different basis and different vector space. Okay. Now, right, if I do this, if I do the tensor product of this, right? So V cross W, okay? What we can do is that we can just use the rules of the tensor product in such a way that they are linear, right? Since they are linear, you can just drag the summation around. You can just switch the summation into the front. Let's just do that, right? Sigma I and sigma j, right? Because they are linear. If you think about just the simplest case where you have just I equal to 1 and I equal to 2, right? Then you're gonna have a summation, just a plus sign in front of in the first bracket and the plus sign for the second bracket, and then you do just your usual expansion. In that way, you can actually have the summation of the two with the product of vi and vj, vi and wj, sorry. And in conclusion, what you have in the end is this, right? And then if we do this, right, because of vi and wj are just a scalar, right? You can just drag around, and the result is in this stuff. Sorry, ei, right? And fj, yeah. So that's it, right? If you do the simple tensor product of two vector space, this is our new basis. All right, our new basis. And in this case, you can clearly see that this vector consists of two vectors coming from a different vector space, v and w, right? And if you combine them using a tensor product, you have this as a component, right? You can have this as a component. Yeah. So you have a component multiplied by the new basis. And what do? You do the summation of all possible bases, right? Sum of all bases. All right. Are we clear? So in this case, where you have psi coming from two different vectors, from different vector spaces, you have a new basis, ei cross fj, and you sum all of the all bases with the component vi and wj. All right. So we can clearly see that the new basis that we want is just all possible value of I and j's, which can be written in terms of the tensor product between two bases. All right. So this is a new basis that we want to work with, because E, you know E, F, you know F from a different vector space. All right. And that is a new basis. And my question, next question is that how many are there actually, right? So
I times j.
exactly. So the new basis, right? Note that the new basis has let's do this first. Sorry, let's do this first. That's a bit too quick. Suppose that this has dimension n, right? So sum is equal to 1 to n, all right? And the f has dimension n, right? So j, that would be 1 to m. Okay. So the new dimension for ei and fj, so the new basis that you need is that you have, sorry, sorry, it's a bit too small. So the number of the new basis is simply n times m, right? Because you have n possibility here, right? I equal to 1 to n, right? J equal to 1 to m, right? So the new basis, you would have the E1, and then you do the tensor product with all of the F, right? So you have M, right? And then E2, you have a tensor product with all of the Fj, right? If you repeated the same process, right, you would have the number of the new basis as n times m. Okay, so that's the thing. You can just write down the new basis as the all possibility of the tensor product between the basis vectors. Okay, so that's the first thing that you need to know. Okay, can I move down? You guys write down everything. Okay, right? Okay.
Teacher, please
Yeah.
wait for a sec.
Yeah.
Thank you,
You want
teacher.
you want to go up a bit, or maybe
Oh man, this
this is
page.
okay?
This page,
Okay.
teacher.
Okay, cool.
Okay, teacher, finish. Thank you very much.
Okay, cool. Yeah. So now we are ready to do some example now, I think. Let's do some example, okay? Oh yeah, I think I should mention this a little bit. Sorry, I take it back. So you can clearly see that the component here, right? VIWJ, yeah. I think I should make a small note. Note that for psi equal to V cross W, right? The component is VIWJ, right? In general, we can write this psi, right? We can write this, and we can write some I, some j, right? And then the component psi ij, which can be any number that you want, and multiply by the basis, right? And in this case, it doesn't have to be the two products. Sorry, the products of the two vectors vi and wj. It can be any numbers. Okay, so this is the general vector. Okay, this is general vectors in the new vector space. Are we clear? So psi can be anything, right? Psi ij doesn't have to be a product of two vectors. right? So it can be just any number. It can be symmetric, non-symmetric, or whatever you want. That's fine. Okay. And I will come back to this point when I talk about the entanglement later. But right now, just think about just a number, right? Basically. Okay. Cool. So we go to example next. Okay. Let's do some example. Okay. So we're gonna go to the classic stuff. Yeah. Let's do something that we can actually write. System of two spin. Right. So basically electrons, maybe, just in case you're not so familiar with other spin yet, right? So two electrons. Yeah. It's a system of two electrons. Okay, so we have a first electron, right? We say that the first electron lives in a vector space V, right? And the vector space V has a basis that you are so familiar with, right? You write that as Z, so Z plus and Z minus as a basis, right? So the first electron lives in the vector space V, which has the basis Z plus and Z minus. You can also write this, okay, if you want to, since we have learned about the angular momentum theory, right? So you have 1/2 minus 1/2. Sorry, yeah. That should be okay too, okay? If you're not remember, right? This is J, this is M. This is J, this is M. So J equal to 1/2, you have two values of M, right? Minus 1/2 and plus 1/2. And that is correspond to the spin half particle, which in this case is the spin of the electron. Therefore, you can sometimes write this as 1/2, 1/2, 1/2 minus 1/2 as a notation we use for the angular momentum. Okay, so you can Z plus, Z minus, that's fine, right? 1/2 minus 1/2, that's also okay. Right, so let's go to the second particle. Okay. Yeah. So the second particle also lives in the same vector space, right? But for generality, I'm gonna say that this is defined as another vector space, right? Just in case. And for generality as well, I'm not gonna use Z plus and Z minus as a basis, just to see the difference. So sometimes you can also use a different basis as well, like this one, right? I can use X. Yes? No problem, right? It's a different basis anyway. You can just use that the same as well. You can just use X, you can just use Y. They're perfectly fine. Okay. In this case, right, if I do some strange notation here, Z and X, yeah, I can do that. The new basis are the following, right? So the new basis, that would be Z plus tensor product with X plus, right? So you just do the simple expansion of Z plus and X plus and X minus. So this is first one, right? The second one, that would be Z plus cross X minus, right? The third one, that would be a bit too big. Yep. And the third one, that would be this, right? X plus. And the fourth one, that would be Z plus, Z minus, X minus. right? So this is a whole set of new bases that we can write, right? This is a new basis. And you can clearly see how many are there, right? If you think about the numbers here, this is 2, right? 2 dimension, right? So the number of bases for the new vector space is 4. So therefore the dimension is 4. Okay. So if you have a system of 2 spins, you clearly have a 4-dimensional vector space, which expand as a basis z plus, x minus, z minus, x minus, x plus, z minus, x minus, for example. Okay. Or we can also write, right? We can use z plus, z minus instead of x plus, x minus as well. Yeah. And if we use that, the new basis are clearly the same, except that you have a tensor product of z and z. Which, look like this. Right? So we can write the new basis as this one as well. And please note that if you want to be more consistent in the way that the first basis and the second basis are different, you sometimes write 1 and 2 here, right? Just to be more careful about which one is coming from which particle. So 1 is from the first particle, and this is from the second particle. Right? 1 means the first particle, second, 2 from the second particle, respectively. Cool. Yeah. So that's how we define the system of particles using the tensor product. Right. Another notation that is going to be useful for you, since we have to deal with a lot of, z plus, z minus, right? Sometimes a shorthand notation is used, right? What do we mean by shorthand notation? Yeah, sometimes if you want to describe the spin of spin half particle, sometimes you use up for z plus, right? You write down the arrow pointing up for z plus, right? And you write down the arrow for the arrow pointing down for the z minus, right? So sometimes we also use this as well. This is because you save a lot of, writing from crossing product, right? Because z plus alone has a lot of, lines, and you have to do cross as well. You have to do 4 times. That's too much, right? Sometimes we write up and down, which is so quick in the sense that you can write down up, and down, and down, and up, and down, and down, right? So you would have 4 bases the same way as the above, but you save a lot of writing in this sense. Okay. Cool. So do you have any problems so far?
No.
Okay, cool. Sorry. So let's go to the next topic, okay? Now we know the vector space, we know the basis, how to write the basis, we know the fundamental stuff that we can do on the vector space. You can add stuff, you can multiply by a scalar, and so on and so forth, right? The one thing that we need to do next is to consider the operators acting on the new vector space, all right? So let's talk about the operators now. Okay. All right. Now we are ready to talk about the product. Sorry, the operators on the tensor product. Let's go back to the first operator. Sorry, for the first tensor product, right? Suppose we have a vector, an operator T, yeah, acting on the vector space V, right? So you have a vector V acting on operator T, you get another vector V, for example, right? So T is the operator in the first product. In the first vector space V, okay? So how can we do the operator acting on the vector space, okay? First of all, you cannot use T as an operator in V cross W, right? That's just wrong, yeah? Because the new vector space that is coming from the tensor product between the two, if you use T lives in a different space, okay? T acts on V only. You see my point? So T acts on V only, right? So this is operator in V only. So you cannot just use T as a new operator in, tensor product space V cross W, right? We have to combine with the vector. Sorry, we have to combine with the operator in W as well, right? We need to tell how a vector or how vectors in transform, right? So basically, instead of using just one operator T, yeah, you have to do the transformation on another vector space as well, just to be complete, all right? So we have to construct the rules in such a way that tells you how the vector in vector space, the first vector space transform, together with how the vector in the second vector space transform, okay? So we cannot use T alone in order to construct how a new operator would look like in the new vector space. Are we clear? So suppose that we want, okay? Suppose that we want to leave vectors in W alone. Right? What do we mean by leaving the vectors alone? Meaning no transformation, right? So if I'm trying to say that the vector in W vector space has no transformation, this is equal to identity operator in the second vector space, right? You see my point? Right? Suppose that we want to act on the first particle alone. I just want to, right? And we are stuck in the position where you have two particles together, but I just want to transform the first one only, okay? And if you want that, left with one condition, right? So I have to combine T with the identity from the second vector space. So if I want to do that, right, let's construct that. Let's construct another operator, right, with the purpose of transforming only V, right? I just want to transform V, and I just want to leave W alone. I don't care, right? So that operator would look like this. Yeah. So this is my choice. Okay. I want to do another tensor product of the operator as well. So T, maybe green, maybe T with the tensor product of the operator with the identity 1, right? This is my object because we want to transform the first vector space with T and the second vector space with nothing. So leave it alone, right? If I want to do that, right, and I try to act it on a vector V, any vector V, and tensor product, sorry, it's not too good. A tensor product W, okay? If I want to act it on this, right? What do I want from these two pairs of tensor product is that I want T to act on V only, okay? I don't want T to act on W because that doesn't make sense because they live in a different vector space, all right? And 1 here would leave the vector vector W alone. That means the laws that I want to construct the whole tensor product thing is that I want T to act on the first vector space, and I want the second one, right, to act on the second vector space. Yeah. So this is what I want, right? I construct T with identity operator 1 that lives in the second vector space. And if I use this new operator acting on the new vector space, I kind of expanded an operator onto the vector space that is suitable for that operator, right? So T would act on V, 1 would act on W. See? So in this way, this makes sense, okay? This makes sense. Are you following? Do you have any problem so far? It's a new concept,
Yes.
so yeah, sure. Go ahead.
I want to know that is the new operator
Hmm.
invariant under changing order? I mean,
Sorry,
T times
change.
I equal to I times T.
No.
No, okay.
No, not at all. Not at all, because T acts on the first on the first vector space, right? And the identity operator acts on the second vector space. All right. And my purpose is to construct anything that leaves the second vector space alone and transform only the first one. And you know that you cannot use T, right? You have to use a pair of two operators. And the only way that makes sense is that you have to transform only the first one. Therefore, I want to make a rule in such a way that if you have two operators coming, you do the tensor product, you have to distribute the operator into the correct vector space. T on V, 1 on W. So if you switch it from 1 to T, right? If I want to use this rule, right? T would act on W, which is not what I want, right? Also wrong, because T doesn't live in the vector space W. All right, so that's not commuting. So that's a good point. Okay. T cross E not equal to 1 cross T, right? Because T doesn't act on W, right? So you don't do that at all. Yeah. And this is the only way that makes sense. Okay.
Teacher, I have another question.
Sure. Go ahead.
So since we define that the spin in such direction is in the v space, and the spin in x direction is in the w space, but we know that we can write the spin in x direction in terms of z direction.
Yeah.
And now we work on only z direction. So can we still say that this is the product of v space and w space?
I mean, yeah. I mean, that's a different thing, right? Because even though it looks the same, it has the same structure, but it means totally different thing. You see what I mean? It's like you have two vector space that looks the same, right? Exactly the same. This is fine, but they are different thing anyway, because one of them would describe the second particle, one of them would describe the first particle, right? Even though they are equal and you are allowed to write V cross V, this is fine, but they are different things. You see my point? It's a totally physical meaning, different physical meaning. Okay, you cannot just
Yeah.
the same stuff, right? Because that's that is responsible for the first particle. That's responsible for the second particle, and they're different things, right?
Teacher, are they different because of the coefficients
What do you
in
mean by
front
that?
of them? Because I think if we write v times v, we
Right?
have one coefficient, and if we write v times w, we have the another coefficient under z direction.
No. You don't think about coefficient with the vector. I'm talking about the structure of the vector space. Okay, so the coefficient that lives in the new vector space is a totally different thing. So, right, let's go back. I think it's a good point. Where was it? Wait, where was it? Yeah, okay, cool. Right. They are different by the meaning of the physical meaning of the particles, right? So you don't actually use the same stuff. And can I write here as the V, right? This is your question, right? Can I write V? It's okay. Yeah. And the coefficient plays no role at this point. Okay. So you can write a vector space V, but we tend not to do that because they're totally different thing, right? It looks the same, it has the same structure, it has the same basis. Yeah, everything's fine. But one of them means is used for the first particle, and the second one is used for the second particle. So you don't actually mix it, right? Otherwise, you will get lost whether or not this one is from the first, this one is from the second. I'm not sure I understand your question now. Sorry. So can you like elaborate more?
Yes, teacher, but if I see the basis that is constructed by Z times Z, how can I determine that this is the product of V space time v space or v space time w space?
The position matters now. Like this one, right? For the first and the second particle, the one before the tensor product means the first particle. The one after the tensor product is the second particle. So now you can differentiate between which one is the first, which one is the second.
Teacher. Okay.
Okay. I don't think I get your point. So if you're still confused whether or not it's the same vector space, my short answer is yes, they are the same vector space, but they have a different meaning.
Okay.
Okay.
Yeah. Teacher, is like that we can write this new basis as the product of v space times w space, but the w space can be equal to v space.
Yeah.
Okay.
Mathematically, yes. Yeah.
Thank you.
That's totally fine, right? I can use the same thing, I can use a different thing, and often than not, you just see the different thing. Yeah, like the typical stuff that we do in the atomic transition, for example, right? You typically combine two totally different vector space. You're gonna see it later. I don't know, not in this course, of course, in some other courses as well. Yeah, like if you want to do the atomic spectra, right? You have to think about the summation of the angular momentum of the system, which contains the nucleus and the atom and electron. Yeah, and the angular momentum, they are not totally they're different thing, right? So you have a spin here, and also the angular momentum of the electron around the nucleus, and they combine. Yeah, and that's a totally different thing. Yeah. So just to be sure, yeah, just they are different, right? In terms of mathematical structure, in terms of the physical structure as well, but they can be the same thing. Sure, that's fine. Totally, we are allowed to do that. But in the physical sense, you have to think about they mean a different thing in the real thing in the physical world. Okay? So I don't want to mix it. Yeah.
Yes.
Cool. So let's go back to the operator, right? So I want to make the new operator make sense. Therefore, I need to write T and the identity in this way with the accompany role in such a way that if you have T and 1 acting on the vector space, acting on the vector V cross W, you have to distribute the operator into the correct vector. So T on the first one and 1 on the second one. Okay. So if we want to use this concept, right, to generalize in terms of the general operator, right? In general, the operator T that acts on the first vector space, and let's say if we have another operator that acts on the second vector space, V, W, right? If we have two operators, the combined operators, the tensor product of T and S, the tensor product of T and S would act on the tensor product space, right? So this is a mapping between the new vector space into the new vector space. Yeah. In such a way that if you have T acting on S, right? And I usually write parentheses here just to be safe. V cross W, right? So the rules is simply distribute the stuff into the correct vector space, T on V and S on W. So you would have this. That's the rules of the tensor product of the operator. Okay. That's what we have for the tensor product space. Okay. Are we clear?
Teacher, can we do the tensor product for more than two space?
Yeah, sure, we can. Yeah. We have 3, we have 4, we have 5, whatever. Yeah. So you mean this, right?
Yes, yes.
Yeah, fine. Yeah. Totally okay. Yeah. We are allowed to do that. Yeah. And the rules, the general rules apply. Right?
Excuse me, teacher. I have a question. Yeah.
Yeah.
In your according, you say that T acts on V only, right?
Yep.
So the vector space has specific operator to act on themselves, right, teacher?
Yep.
So it's common rule, right, teacher?
Exactly. Yeah. Yeah.
Okay.
This is the rule that we want, because even though you try to think about the special case, like Haran said earlier, right? If W vector space is equal to vector space V, yeah, in principle you can switch them, but that's not nice, right? Because we want to talk in the general case, right? And the only rule that makes sense is to distribute the operator in the correct vector space. Yeah.
Okay,
Yeah.
teacher.
If you switch it, then you're gonna screw up in the general case right away. Okay. So this is the only way that makes sense. Yeah.
Thank you, teacher.
So cool. Any question? It's a different aspect of the vector space as well. So you should be more careful on how to use them, right?
Teacher, so
Yeah,
although we have any number of space that we work on, we have
sure,
to preserve the order and operate it by order, right?
exactly. Yeah,
Okay, thank you.
yeah, yeah, yeah. So if you have 3 particles, right, you have to make a label clear that this one is the first one, this one the second one, this one the third one, or whatever. And the order of the tensor product, you have to make it clear at the beginning, right? And you work out on that order. Okay.
Thank you, teacher.
Yep. But you're gonna be confused later on if you think about the correct order if you have the identical particle. But let's forget about that for now. Okay. Yeah. You have the whole thing about symmetric, anti-symmetric stuff. I think you probably learn in the wave function version as well, but you also have this version of the tensor product. But I don't think I can make it that far. uh, let's just say that we can label them, okay? And that's good enough for this level. Okay. Right. So the next point that I want to mention is that in this way, all right, we can actually write T, yes, right, as this. Ah, Okay, I can actually write this. What do we mean by these two things, right? So this is tensor product, okay? That's clear, okay? This is tensor product. And this is the succession of operators, right? Successive operation, right? What do we mean by successive operation? It means that if I have this as acting on V cross W, okay? If I write this literally, I have this, right? Acting on this, which is acting on this first, right? So the rules applies that if you have a two successive operation, you just write them together with another dot or something, or you don't actually need another dot. I just want to make it clear that they are two different things, okay? This is a successive operation. So you do this first, right? First, and then do this later, right? You do from right to left as you normally do for the two vector, right? Let's say ST, sorry, I think I should use, I don't know. Okay, ST and vector, right? So you can actually write S acting on T and V. You see what I mean, right? If T is close to vector, you act T on vector first, and then S later. So sometimes you write the parentheses, sometimes you don't write the parentheses. This is the case. So what do we mean by this is that I use this as the first operator and acting on V and W first. And if we do that, right? If we do this, what do you get by applying the general rule of the tensor product of operators? You have this, right? You distribute them, yeah? And 1 on vector V is vector V. Clear, no? And the cross product would act on the S on W. Okay. Are you following? No? So 1 on V, you get V. S on W, you get SW. Okay. And if you repeat the same thing for this operator, right? T would act on that, 1 would act on that. You would get this, right? T on V cross with S on W, which is the same thing as the above, right? So you can clearly see that instead of writing T with S, right, cross product of T and S, it kind of mean that you do T and S separately, right? So what do we mean by this? I think I should move this to the next page as well. Shit, sorry. So are you done writing down in your note? Okay. No answer, so I can do this, I guess. So everything you need to write down is in this page, correct? Okay. So if you write this, right, T cross S is equal to T cross 1, and then, sorry, 1 cross S, right? It's actually mean that we can transform S alone sorry, alone first, and then transform V alone later. Okay, so it means the same thing. T crossing do the cross product with S, right? T cross S, it means that you can just do S on the second vector space first, where you keep where you keep the first vector space invariant, and then after doing that, you do the different thing where you transform the first vector space and keep the second vector space alone. Okay, so that's actually mean the same thing as T cross S. Are we clear? That means that if you want to do the different order, it should look the same as well, right? Because we leave the other vector space alone when you apply S or T operator. So therefore, you think about it. T cross S is actually the same as this. Sorry, T cross 1. All right? Because each of the operator here, T cross 1 or 1 cross S, it leaves another vector space alone. Therefore, if you can change the order, it doesn't really matter because the other one is 1, right? So you can clearly see that you can actually check this as well, right? If you want to do the whole stuff, but I'm not going to repeat it because I haven't the physical argument here, because the other one is just the different order of the operation, right? So in this case, right, you can clearly see that this is commuting with this, right? The order doesn't matter. Yeah. So the commutator between T and 1 and S are commuting 0. So you can write that as a commutator between them is 0. Okay. Another way to look at the stuff like this is this. Okay. The successive operation works in the order as this one, right? So let's suppose that we want to work out with T, I don't know, 2 cross S2, right? And before that, you do T and S1, right? This is the same as this T2, T1 cross S2, S1, okay? So the successive operation, if you want to work on that, is nothing more than just applying to the correct order, right? So let's check that. Let's check this, okay? Suppose that I want to act this, right, on some vector. Sorry. Yeah, if I want to act it on one vector here, and this would be this, right? T on V1 cross S1 on W, right? And then you act again using the typical distribution of the operator, right? You get this. Yeah, are you following? So you distribute T2 to that vector and S2 to that vector, right? You get this. And this is equal to T2, T1 cross S2, S1 on V cross W. Okay. So the successive operation works like that as well. And that's how we do the tensor product of the operators. Good. Okay.
Teacher,
Yeah.
actually we can drop the dot sign and
Yeah.
also
Yeah.
write one, right?
Sorry, say it again.
I mean when we drop the dot sign and we write the dot, it's the same meaning, right?
Yeah. So you don't actually have to write it, but I want to make sure that they are just a product, like a product of vector and operator. So you don't normally write it, right? But I just want to make sure that they are just a product. It doesn't matter. Yeah, it doesn't matter. You can just drop it. Yeah. Sometimes I have a habit of writing a dot product. Sorry, a product clear, because you have too many type of products now, right? And sometimes it's kind of confusing whether or not I should write something close together and interpret that as a product, right? So it's kind of confusing as well. Sometimes I write dot just to make sure that you see which one is which. Yeah. But yeah, if you don't normally write it, you don't have to. Yeah. Okay. Cool.
Okay, teacher, thank you.
Yeah. So now we are ready to discuss some physics now, right? Because we have all the rules of the tensor product. We have the tensor product of the basis. We have tensor product of the vector. We have tensor product of the operators. Yeah. So we are ready to work on the physical meaning of it now. Okay. So the first and simplest question you can ask, right? Suppose that I want to measure the energy of a system. Okay. What do we actually do? So let's suppose we have a system of one particle, right? I don't know, so just one particle, right? And let's say a system of particle, a system of one particle here is luckily is in one of the energy eigenstate, the Hamiltonian one. Okay. Let's say we have E. So if you want to know what is the energy of a particle, how do we do? You do this,
Apply
right?
Hamilton.
Exactly. You use H on the set side, and that would give you the eigenvalue, which we can measure, right? By finding the average and so on and so forth, whatever, right? So this is how we measure the energy of the system of one particle. Okay. Now the question is, what about two particles? How do we do? Let's say that we have a system of two particles, right? And maybe just to make the example more clear, let's say that a state is in the energy state 1 of the first vector and product with the energy state 2 of the second vector space, right? Let's say that E1 and E2, right? How do we want to measure the total energy of the system? How do we construct the total Hamiltonian, basically, right? Yeah. Can I do this? Does it make sense?
I think yes.
Let's try, right? What do we actually want from the total Hamiltonian is that if we applied it to the state, you should get the total energy back. Yes, right? The total. So let's do that, okay? Let's check. Let's do H total on psi. Yeah, H total on psi is this. E1, E2, right? What are the rules of the tensor product again? You distribute it to the correct vector, right? E1 and E2. Yeah. And now, if we have this, H1 on E1 is the energy eigenstate of the H1 operator, which is E1, right? H2 on E2, this is the energy eigenstate of the H2 operator, and the result is the eigenvalue E2, correct? And if we do that, what happened? Because E1 and E2 is a scalar, right? You can just drag out it at the front and write down as the common factor of E1 cross E2, right? So the eigenvalue state of this is E1 times E2, you see? So if you write that as the H1 cross H2, you're going to have the total energy as E1 times E2, which is not what we want, you see? So not E1 plus E2, right? We expect to have E1 plus E2, you see? Because the total means a summation, yeah? So it's clear that this doesn't work. Yeah, you cannot write the tensor product of H1 and H2 and expect to have the total energy. Yeah, so this is not what we want. Do you have any question on this? Good, right?
Yes,
So
teacher, can we do sum square rule?
Sorry, what do you mean by sum square?
Teacher, I mean หน้ากำลังสองบวกสองด้านหลัง sorry.
I don't think I get what you mean.
Okay, teacher, let's go ahead.
Okay, sure. So the correct version, right? Let's say that the correct one is this. The total Hamiltonian, right? The total Hamiltonian is this. I think I should write it down like more carefully. The total Hamiltonian is this. Yeah. This is the correct one. Why? We can check, obviously. Yeah, let's check that. if we do this, right? If we apply the total Hamiltonian onto the tensor product vector, what you're gonna have is the whole stuff here, h1, right? Cross 1 plus 1 cross h2, yeah? Acting on v, sorry, we use e now, right? e1 cross e2, yeah? And now if we do this, we can expand it, of course. You would have this h1 cross 1 on e1 cross e2, right? And then 1 cross h2 on e1 cross e2, yeah? And if you apply the typical stuff, yeah, this and this, this and this, you have h1 on e1 cross e2 because the second vector is acting on the identity operator, and the first one, the second term would be e1 cross h2 e2, right? And we do this, you get e1 on e1 cross e2 plus sorry, plus e2 on e1 cross e2, yeah? So if we factoring out everything, you can see that the vector e1 cross e2 is the eigenvector with the eigenvalue e1 plus e2, right? So this is what we want because this is the total energy, right? So therefore, whatever you want to work out with the Hamiltonian, this is the version that we want. So we do h, we do h1, we do h2 separately, and then combine them. Okay. Do you have any question?
No.
Cool. Thanks. So can I change the page? Can I go to the next page now? Maybe it's, I can wait a bit, I think. Can I go to the next page?
Yes, teacher.
Thank you. Okay, nice. So, okay, that's good. We now know how to combine the operator, right? But please note that for the evolution operator, right? For the evolution operator, whatever you want to do, let's say that this is the simplest case, right? H and T U T. I think I write T is T0, right? Yeah. Minus I over H bar H on T minus T0, right? So for the evolution operator, yeah, if we combine that and use it for the multiple particle state, what we actually do, we do not combine them, all right? We want the evolution operator to act on each state simultaneously, right? So we typically want both state, both particles to evolve together. Yeah. So therefore, if you want to evolve both particle to, let's say, a total of U, like, what should I write? Total, maybe? I don't know. Yeah. I shouldn't say total. I should say U system, maybe. Yeah, that makes more sense, right? In that case, right, I have T T0 cross with U2 T T0. Okay, we want them to evolve together, not separately and then combine. Okay, so only this case where you want to apply to both states simultaneously in such a way that if I want to work with the evolution of a system acting on some kind of tensor product state, that would be U1 acting on U2. We at time 0, maybe, I don't know. Yeah, cross with W at time 0, right? I would end up with this U1 on VET0, right? Crossing with U2 on WT0, and that would lead you to this. Yeah, so this is what we want. The system, the system version of the time evolution operator is the tensor product between the two, because we want both operator to act on the state simultaneously, right? We don't want to combine value or something. We want them to evolve together. So that's why we need this version. You can actually check that this is what we want by, expanding in terms of the Hamiltonian and stuff like that. That's also okay, right? So we can actually check that U system is nothing more than what you know, and sorry, H total, right? You can actually write that as well. Where H is what we have already, which is H1 plus 1 plus 1 cross H2. Yeah, we can actually check that. I'm not going to show you how, but it's just a simple manipulation of the exponential version of operators, right? So, and that's not so important. So that's where I'm going to leave it with. Okay. Cool. All right. So far so good, no? Do you have any problem? Question? No? Okay. Nice. So I think we should have a break. How about 10 minutes break? How does it sound?
Good teacher. Very nice.
Okay. Yeah. We should have a break now for 10 minutes and then we come back and I'm gonna finish the multiple particle states, okay? And a little bit of angular momentum as well, which is like tiny bit. So that's nice. So let's have a break and we come back at 15:25 maybe. All right. So yeah, 15:25. Yeah. See you later.
Thank you, teacher.
Hello. Are you guys coming back? Okay, so I think I should start now. Do you hear me? You see my screen?
Yes.
Okay, nice. Right. So now we are ready to work with the example. Okay, let's do some example on the spin. Okay, let's work on two electron system. Okay, uh, the same as before, right? We have the first electron, right? We have the second electron. Okay, and we have a first basis, right? Vector space 1 with the basis, which now I'm going to use up and down. Okay. V2 also has a basis, which I'm going to use as up and down. Okay. So this is the basis that I want, up, down. Okay. Now you can think about this as the Z direction plus and minus. Okay. So these two. Okay. Let's think about that as the Z direction plus and minus. Yeah. And maybe plus and minus also work. Uh, should I use plus minus instead of up and down? And because I'm gonna do plus minus in the meaning of direction as well. Yeah, well, I don't know. What do you want? I can also make this, right? Or sometimes we also do plus and minus here. Okay. It's basically the means the same thing, right? But depends on what you like. So which one you guys want to do? Up and down or plus minus?
Teacher, I'm okay for all.
Okay, okay. So now let's stick for up and down, okay? But if I think about the number of stroke that I have to write is 1, 2, 3, 1, 2, 3. Yeah, okay. Not too bad. Okay, let's stick with up and down, okay? And think about up and down in that direction. Okay. This is what you need to think about. Okay. This is what it means, basically. Right? Now we are ready to do the vector space, right? The tensor product space V1 cross V2, right? The bases are the following. You have up, 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 down, down, up, and down, down. Okay. So these are 4 bases that we need to construct. Okay. And this is the stuff that we want to work with. Now let's talk about the state. Okay. The general state is written as psi, right? Since this is a general state, I typically write 4 coefficient, right? With the basis here, right? Alpha 1 times up, up. Alpha 2 times up, down. Alpha 3 times down and up, right? And alpha 4 down and down. Okay. So this is the general state in the tensor product space. Okay. Now we are ready to work with the spin. Okay. Now let's work with the spin. Yeah. So for the spin, if we have the spin as that, right? The spin as that, if you act it on up, right? You get plus h bar over 2 and up, right? For the down one, you get minus h bar over 2 down, right? Are we clear? So up means that plus, right? So basically this is that plus state. This is that minus state. Therefore, the eigenvalue of S SAT operator is minus h bar over 2. So this is a case for the up and down state. And can we work with Sx as well? What do you have for Sx? You know this one? So Sx, right? That would be h bar over 2 and down, right? Are you following? Yes, no? Okay. In the Z plus, Z minus basis, yeah, the operator would look like this, right? And up, that would look like this, right? So if you add them together, you get the h bar over 2 and down. You see? So this is what you have. And similarly, if you have Sx and down, you have h bar over 2 and up, right? So these are the rules on acting the spin operator, using the spin operator acting on the state up and down. Okay. For Sy, you can do the same with I and minus I and whatever, but I don't care now. It's the same principle on calculating this thing. Okay. So cool. So the spin operator, we have the spin operator for each particle, right? For spin operator acting on one spin, you know how it goes, right? Now we gonna do the combined spin operator. Okay. Okay. Now we are ready, right? Because we want to work with the total spin in, let's say, that direction first. Okay. Okay. How do we do? We use the same principle as the total of the Hamiltonian, right? We do this spin for the first particle plus 1 cross the spin for the second particle. This is what we mean by this total spin operator, okay? Right. So the total spin in z direction can be written in terms of z spin in z direction for the first particle combined with the spin in z direction for the second particle, this way, okay? Now we are ready to act on everything, okay? Let's apply this onto the basis, okay? Since we know that we have to apply it for the general state, right? So we're going to do basis by 1, 2, 3, 4. That's going to be easier because you calculate everything right away, all right? So let's apply onto the basis first. Let's think about this, right? Applying onto up and up, yeah? What do you have? If we use the same rule, right? SZ cross identity plus 1 cross SZ acting on up and up, yeah? You have two terms, S on 1, up and up, right? Plus 1 cross S, Z, and up, right? And if you use the usual rules for the tensor product, you would get S, Z on up, cross up, right? Plus up, cross S, Z, up, right? And both of them would get h bar over 2, right? So you would get h bar over 2 up, cross up, plus up, cross h bar over 2 up, yeah? And because we have the rules for the tensor product, right, that the scalar multiplication can be moved around, so h bar over 2 is clearly a common factor. Therefore, sorry, up and up are clearly the common factor. So therefore, you can do this, right? Right. If you combine them, you get h bar up and up, right? See? So now we are pretty sure that the angular momentum, sorry, the total spin in that direction for up and up state is h bar, okay? So if you think about this as the eigenstate, right? the eigenvalue is h bar. Yeah. So therefore, you can clearly see that the total spin in z direction of up is h bar, right? And this kind of work, right? Because we have the clear picture now, right? If you think about the pictorial stuff, right? So if you have this first spin in z direction, which has the value of h bar over 2, you combine that with up, which has this total spin in z direction as h bar over 2 as well. You combine them, right? You have a kind of a particle with the total spin of h bar, right? So you have a system. I shouldn't write a particle. But you have a system, right? With the total spin of h bar. Yeah, because the spin are pointing in the same direction. You see what I mean? Because they are up and up, right? And their spin combined. When you combine the spin, the total spin is h bar. This is a physical picture for the total spin for the up and up state. Okay. Are you following? Do you have any question?
No.
Can I change the page now? Right?
Wait a minute, teacher.
Sure.
Thank you, teacher.
Yeah.
Okay, teacher, I'm done. Thank
Cool.
you.
Cool. Right. Now we know the total spin for up and up, right? Let's do this. Let's do down and down. Okay. It's pretty much the same thing, right? I'm not gonna write it down because we know what happened if we do up and up, right? So up and up, you get plus h bar over 2 plus h bar over 2. If you do the same thing, yeah, you're gonna get minus h bar over 2 plus minus h bar over 2, right? It's a very straightforward calculation, so I'm not gonna repeat it because this is pretty much the same thing, right? So we can clearly see that the total angular momentum for down and down state is minus h bar. Yeah. I leave it as an exercise. I think you should be able to repeat the calculation. Okay. So therefore, down and down as the total spin in z direction equal to minus h bar. Yeah. And it's the same thing, right? We interpret as the eigenstate. Yeah. And this is the eigenvalue, right? So down and down has a total spin of minus h bar. And that also makes sense, right? Because if you have the spin of down, right, the spin in that direction is minus h bar over 2. And if you combine that with another particle with the spin minus h bar over 2, you combine them, you have the system with the spin minus h bar, right? That makes sense. This is a physical picture we have. Okay. Now we know up and up, down and down, right? and they clearly follow the same structure that we have. How about SAT total on plus and minus, right? What happened if I do plus and minus here? If I do plus and minus here, right? If you follow the same step, right? You should get minus h bar over 2 plus h bar over 2, right? So if I do the same stuff, I should get, sorry, the first one should be plus h bar over 2, right? The second one should be minus h bar over 2. And you get up and down, okay? And this means that the eigenvalue is 0 because they cancel, okay? And similarly, if we do the opposite one, which is down and up, yeah, you should get the same thing, right? So you should get minus h bar over 2 plus h bar over 2 onto down and up. This is also 0, okay? So therefore, you can see that up, down, and down, and up have no total spin, sorry, in z direction, right? So therefore, if you have up, if you think about the picture that you have plus and minus h bar over 2, combine them, you get 0, okay? So that's no spin. And the other way around for down and up as well. So this is how it works, okay? So that's nice. We now calculate the whole thing, yeah? Right, do you have any question? So far, so good, right? We understand how it works. Yeah, yeah. Sorry, go ahead.
No, teacher, I don't have.
Okay, cool. Right. So now we are ready, I think, to understand some more fundamental concepts. Oh no, not yet. How about SX total? Okay, let's do SX total. Let's see how does it change in terms of plus and minus, sorry, up and down. So if we want to do the total one, right? What do we have? We should have this, no? We should have SX cross identity plus identity cross SX. All right. So how about this? If I do S total on up, what do we get? We have to do the whole thing, right? So we have to make SX tensor product 1 tensor product with SX on 1, 1, right? And then if you expand it, you have SX on up cross up plus up cross SX on up, all right? So I skipped some few steps, but you can follow, right? You can expand it into the parentheses and apply the operator into the correct vector. And this is very simple because if you apply up and S total for up and up, you get h bar over 2 down, down and up plus h bar over 2 up and down. Yeah. So you doing that, you get what? You get this, right? H bar over 2 down up plus up down. All right. Cool. Nice. So how about this? S total on, let's say, down and down. All right. I have to calculate the whole thing again, right? But you want me to do it explicitly? It's not so obvious, I guess. Yeah, let's do it up explicitly, okay? But more quickly, I guess. Yep. Let's do this, okay? Sorry if you writing down on your notebook. I'm cheating a bit. So we do down and down, right? So if you expand the whole thing, you have Sx on down, plus down on, sorry, Sx on down, right? So that would mean that you have h bar over 2 up, down, and up, right? So Sx on down and down, you get the same thing. Yeah. Right? Cool. Are you done writing down? Can I go to the next page? I can, right? Yeah. Okay. Cool. How about Sx total on up and down? Right. You can guess, no? You can also do the whole calculation again. I'm not gonna write everything now, so I'm gonna do it quickly. So now we have Sx on up with down, right? And up on Sx down, right? So if you do that, you have a common h bar over 2, and you would have down, down, plus up, up, right? And the total for down, up would look the same, right? So I'm not gonna write it down again. So everything would look the same except that this is up first. But yeah, you know that, right? Down, down. So are we cool? Yeah. Nice. Right. So now we are ready. Okay. Because Sx is kind of messing up with the up and down structure, right? If you apply Sx into up and up, you get a mix between up, down, up, right? And if you apply Sx to down, down, you get a mix between up, down, and down, up as well. And if you apply to the Sx to the up and down, you get up, up, or down, down, right? So that's kind of the messing up the structure of Sx with the up and down things, yeah? So now we are ready to calculate some particular state, okay? So let's ask some important question, right? Let's find the state in V1 cross V2. So let's find the state in the tensor vector space, tensor product space, okay? Such that S total. On this up state, you get H bar, sorry, H bar and up. All right. And S total. Sorry, I think you shouldn't write this. It's a bit misleading. Let me find one thing first, okay? Such that there is no spin in no total spin in Z direction and X direction. Okay. So what do we want? I want a state in such a way that you don't have a total spin at all. Okay. So no total spin, right? And Y direction as well. But it's clear that if you forbid two of them, one of them would be gone as well. This is left as an exercise, but I'm gonna do that. Just spin the state in such a way that there's no spin at all. Okay, there's no spin at all. So how do we do, right? How do we do? It's clear that it's not up and up and down, right? Because up and down, it clearly has some spin left, right? Because up and down, you combine them as such, still has a spin of H bar and minus H bar, right? So in order to work with that, yeah, let's work with the, I don't know, some total, the general case, all right? Yeah, it's clear that this state up and down is not what we want because they contain the spin itself somehow, right? So in order to prove that, let's check the general case. Yeah, let's check the general case. Let's check the general case in such a way that you have psi, right? 1, up, alpha 2, up, down, alpha 3, down, up, and alpha 4, down. Okay. And the requirement is what? We require that SZ total on psi is 0. Yeah, we apply this and we require that they are 0. Okay, and we work on some of them already, right? Because if we use the requirement here, yeah, S total on psi, that would be alpha 1, right? S total on up and up. Yeah. And the second term that would look like S total on up and down. And alpha 3, that would be S total on down and up, right? And alpha 4 times S total on down and down. Yeah, on down and down. Yeah. Now, if you apply all the requirement, right? We require this to be 0, right? We require this to be 0. And what do you get from this and this again? we find the S total of up and down and down and up to be 0, right? This is 0, clearly. Yeah. What is this S total of down and down? Minus H bar, right? And down and down. Sorry, I think I should write minus H bar. Down and down, right? We did that. Yeah. And what about this? H bar up and up. Yes. Right. So therefore, you apply all the results that we just did. We have alpha 1, H bar, up, up. Yeah. And sorry, I think I should write down here. Minus alpha 4, H bar, down, down. Right? Down and down. Yes. Sorry. So are we clear? Do you have any questions so far? Cool.
No.
Okay. So therefore, the requirement that the left-hand side should be 0, the only thing that works is that this implies that alpha 1 equal to 0, alpha 4 equal to 0, right? So you shouldn't have up, up, and down, down, which is what we actually claim at the beginning, right? Because up and down is not what we want. It contains some spin. If you apply them, clearly that's not the case. All right. So therefore, the state that has no spin in z direction is this. Alpha 2 up, down, and alpha 3 down and up. Yeah. Cool. So this is a state that has no spin in the z direction. Now, what do we want? We want this state that has no spin at all, no spin in x direction as well. So we can apply it a little bit further, right? Let's say that the state has no spin in x direction also. So what do we have? We should have this, right? As total on psi with no spin in that direction should be 0, right? This is our requirement. We require that this is 0. It has to be 0, right? So in that case, you can just use the result that we just did and apply to up and down and down and up, right? Yeah, we also require that, no? So if we require that, we apply this as total on the spin with no set, right? That would be a copy somewhere. That's okay. Alpha 2 on x total onto up and down, right? And alpha 3 on x total on down and up. Okay. And the requirement on the left hand side is 0, right? So this is good. And the right hand side, we also have done that because Sx total for up and down is, sorry, where's it? This one, right? So you would have h power 2 down and up, right? For up and down. And Sx total for down and up, you get h power 2 up and down and down. So if you apply that result, right, we have alpha 2. I think I should write h power 2 right away. Okay. And up plus down and down, right? Plus alpha 3 h power 2 down and down plus up and up. Yeah. And if you combine that in terms of the vector in the new vector basis, you would have h power 2 as a common factor, which I don't care, right? And then for looking for up and up, you would get alpha 2 plus alpha 3 times up and up basis, right? For down and down, you also have the same coefficient, which is alpha 2 plus alpha 3. Down and down, right? So now we are coming to the end, because if we require the left-hand side to be 0, the coefficient to be 0 has to be 0. Coefficient with the basis has to be 0 as well, because up and down are linearly independent. All right. So this has to be 0. This as well, which is the same thing, right? So the requirement in the end is that alpha 2 plus alpha 3 has to be 0. Therefore, alpha 3 has to be minus alpha 2. Right? Therefore, the state that has no spin in x and z direction is alpha 2 and alpha 3, and we replace alpha 3 with minus alpha 2, right? So alpha 2 with up, down, plus alpha 3 with down and up. Yeah. And this is simply alpha 2 up, down. Sorry? Alpha 2, then up, down, minus down, up. Right. Do you have a question? Okay. Okay. So basically, if we want to write a state with no spin in x and z direction, that would look like this, right? Hello.
Yes.
I think okay. Yeah. Okay, that's cool. So this is the end of the line because we have the state with no spin in x and z direction, right? So this you can clearly see that this combination where alpha 2 is just a constant has no spin, right? This is left as an exercise, right? We can check that this state has no spin in y direction as well, right? So what do we mean by that? If I write sy total as sy cross identity plus identity cross sy, yeah, and if you apply to this, right, you're gonna see this always you get 0. Okay, we can check that sy total on psi with no x and z is always 0, right? We can totally check that. How, you may ask, right? So you need this. If you want to calculate this, you apply sy on plus, right? If you apply sy on plus, you have minus I h bar over 2 down. And you if you apply sy on on down, right? You get I h bar over 2 up, right? And you can do the whole calculation again to check that this state has no spin at all, right? So we can also check that. Okay. Yeah. Cool. Do you have any question?
No.
Okay. I have a few stuff left because we're gonna go overtime. Are you okay with that? Maybe 40 minutes, maybe. I don't know. Yeah. Let's aim for 5 p.m. Okay. And I also have another lecture left that I have to talk about on the angular momentum, addition of angular momentum. So I don't think I can finish today, I guess, which is good. Just we have too many things to say. But are you okay with continue on for maybe 40 minutes, I guess? Okay, right? Yeah, nobody answer anything. So I'll go on. Sorry, is it too quick to change the page? It's good, no? Okay. Right. So the last point on this thing is that how do we find alpha 2? Yeah. How do we find alpha 2? It's the same story as the one state particle, for the state of one particle, right? We have to find it through normalization. Yeah. And if you want to do normalization, you have to talk about the dot product, right? We have to ask about what is the inner product of this state, okay? Of this state. And it's pretty much the same stuff that you expect to see, all right? So let's say the inner product of the of the tensor product space, okay?
Excuse me, teacher. Can
Yep.
you go for a second?
Oh, yeah, sure. Sorry. Yeah, sure.
Okay, teacher, thank you.
Cool. Yeah. So let's talk about the inner product. So the inner product of the tensor product vectors. So you do tensor product, also do inner product again, right? So the rules is very simple. The rules is very simple. Yeah, but I don't think I can make it on Wednesday morning now. So let's finish as much as possible today, okay? And then the remaining stuff we can talk on Wednesday afternoon, I guess. I'm not sure what time, so I'm not sure that I can do from 1 to 4. All right. So let's aim to finish as much as possible today. And if you are in a hurry or something, you can just left now, and we have the recording here, right? So you can just follow after you come back or something. Okay. Sorry about that.
Okay, teacher.
Yeah. You can go. Yeah. It's a maybe 30 minutes or something, but that should be it. Yeah. So the inner product of the tensor product, right? The rules is very simple. The rule is this: if we have the dot product with this, right? Yeah. If we have the stuff that looks like this, and you want to do the inner product between the tensor products, yeah. The only thing that makes sense is that you have to pair them up in the correct order, right? Yeah, agree? Because V and V prime, the only thing that makes sense is that they dot together because they live in the same vector space, right? So you have to pair them up in the natural order V, V on V prime, right? And this is the scalar product now, right? This is a scalar, so you can write this as well. Yeah. So the rule is very simple. If you have anything dot with anything, you drag them into the natural order. So the first the first of the tensor product, they should go together. The second of the tensor product, they should go together. You just pair them up, right? So that's very simple. So in that case, all right, the orthonormal basis, the orthonormal condition of EI and FJ, right? EI and FJ, yeah, is very straightforward. So if you have, should use IJK, yeah, whatever, right? So if I have this, let's say if I have EI, right, cross with F N maybe, dot product with EJ with FM. Right? The orthonormal condition of this is straightforward because this is nothing more than just EI dot EJ times FN dot FN, right? And due to the autonomality of E and F, this will become delta I, delta J, delta IJ, and delta NM. Yeah. So this is the orthonormal condition for the tensor product space, basically, right?
Teacher, according to the top equation, why we have to label prime vector since we have already changed bar to cat?
No, this is a different vector, like another vector dot with another vector. They don't have to be the same,
Okay.
right? Yeah. I'm not talking about the total, the norm square, stuff like that. I just talk about the general rule of dotting product, right?
Teacher, and what about adjoint operator?
What do you mean by adjoint operator? The tensor
That
product of adjoint operator?
I mean, if I have
Yeah.
cat v time cat w, if I want to find the data of itself, can I change bra to cat and
Yeah.
that's all?
Yeah, the same thing. Yeah, the same stuff.
Okay.
Yeah, the
Thank
same stuff. So this is a typical rule that you have because we want to pair them up correctly. So for the cat space, you change into bra space of the same vector space, right? So that is why I pair them up correctly. V prime with V, W prime with W. Okay. Otherwise, it doesn't make sense. Yeah.
Teacher, and
Right.
the order of v and w, it should be changed or not?
Well, which one? Sorry.
I mean, if I have cat vector of v times w, if I want to find the data of itself, it
Right.
should change the order or doesn't
Ah,
change.
you mean like, can I write this? Sorry, maybe green. Can I write this? Right? Can I write? Yeah, like this one, right?
Yes.
No, we don't do this because we want to pair them up. First component with first component, and the second component with the second component.
Okay, teacher.
Right.
Thank you.
Yeah. Okay. So that's good. Now we have the autonormality and stuff like that. Now we are ready to find alpha 2. Okay. In order to find alpha 2, let me copy the whole thing. Okay. Is it? Yeah, just do it. We can find it from the normalization. Okay. So the normalization that we are talking about is this, right? We want the state psi with no x and z direction spin to be equal to 1, right? Therefore, we need this as 1. Yeah, we need this to be 1. So what do? We apply the whole thing, right? So 1 equal to this, right? So we have alpha 2 star. We change from ket to bra, right? From ket to bra, you keep the same structure as I said, right? So up and down, that would be up and down in the ket version. And down and up, that would be down and up in the ket version as well. Sorry, that's too confusing, right? And then dot with alpha 2 with up and down minus down and up, right? So if you do that, you have alpha 2 square. right? And then if you expand everything, you're gonna see this, right? Dot with up, sorry, up and down, right? So the first one with the first one, and then the second one second one with the last one, right? Yeah. And then we have this as well. We have down, up, dotting with up and down. And then the last one would be down, up, dotting with down, up. Okay. So it's a simple expansion. Okay. And if you do it correctly, you should have alpha 2 square, right? Multiply by this, up, up, down, down, right? Because we pair them up like this. Yeah, we have to pair them up with the dot product here. And the second term, that would be up and down times down and up, right? Because we have to pair them up like this, right? And you don't have to calculate that because they are 0, right? Up and down is z plus, dot with z minus, always 0, right? Because they belongs to the different eigenvalues of s, z, right? Similarly, on the third term, you have down and up times up and down, which is always 0, right? And I pair them up correctly this way, right? And the last term, you have plus and down, up and up, right? And I have paired them up front with front, back with back. And that is very simple because this is 1, this is 1, this is 1, this is 1, because they are all always normal, right? So your answer should be 2 alpha 2 square, right? And if they are equal to 1, right? Therefore, alpha 2 is 1 over square root of 2. Yeah? That should be 1 over square root of 2. Yeah? And if you write alpha 1 equal to square root of 2, therefore the state that we are actually talking about with no spin is basically 1 over square root of 2 up, down, minus down, up. All right? So this is a state with no spin at all. Okay? With no spin at all. Okay? So this is how you calculate the dot product between the two tensor product vector space. Okay. All right. I think I should stop here. Yeah. We have a few stuff left to talk about the multiple particle states and also an addition of angular momentum. But now I think it should be okay. Yeah. We can talk about it next time, Wednesday. Yeah. Sorry. Yeah. So do you have any question?
No.
Okay. Cool. So Wednesday, if I can start at 1, I'm gonna tell you, all right? I'm not sure now. But if I cannot, I will tell you when I can start. But typically we can start at 1 to 4, since we don't have you guys don't have a class on Wednesday from 1 to
Yes.
30, right?
Yes.
Yeah. I'm not sure I'm gonna come back at 1 or something, but if not, I'm gonna tell you. But definitely 2:30, I should be able to come back and teach. So let's aim for Wednesday first, okay? Yeah. Okay. If you don't have anything left, I'm gonna stop recording first, okay?